All right, guys, Mr. Antonucci here, and in this third video of three, we're going to talk about how to connect position, velocity, and acceleration of an object along a line. And we can often use the first derivative test to investigate properties of motion of an object on a line. Now, we talked about this a little bit in the previous video, but I'm just going to review it here to make sure it's fresh as we use this. So if you have an object moving along a horizontal line, and similar things would hold true if it was a vertical line, its position x at time t is given by the function x of t. And assuming x of t is continuous and twice differentiable, we have the following results. Here's one thing, dx dt, the derivative of the position function, is the velocity function. And the second derivative of the position function is the derivative of velocity function, which is the acceleration function. Okay. Now, if the derivative of position is positive, that means velocity is positive, and the object is moving to the right. If the velocity is negative, then the object's moving to the left. If the acceleration is positive, then that means the velocity is increasing. And if the acceleration is negative, that means the velocity is decreasing. But here's the thing that kind of throws a wrench in this is when we talk about speed, because oftentimes you'll have a question asking, is the speed increasing or decreasing? Okay, so if velocity and acceleration have the same sign, speed is increasing. In other words, if they're both positive or both negative. If velocity and acceleration have opposite signs, then speed is decreasing. Okay, so that means if velocity is positive and acceleration is negative, or velocity is negative and acceleration is positive, then the speed's going to be decreasing. Just a real quick way of how to do that. So for number 4 here, we have an object moving along a horizontal line again. X of t is t cubed minus 9t squared plus 24t minus 5 for 0 to 6. We want to find the intervals where the object's moving to the left. So for this one, to figure out where it's moving to the left, we've got to look at the velocity function. So for part A here, the velocity function is the derivative. So 3t squared minus 18t plus 24. And then we could factor this. So factor out at 3, you get t squared minus 6t plus 8. Set that equal to 0. Factor that, you'd have t squared minus 2, or not t squared, just t minus 2, and then t minus 4. You need to add to negative 6 and multiply to 8, which they do. So you would have t equals 2 and t equals 4. Because this is a continuous function, the only way the velocity is going to pass through 0 or going to change sign is if it passes through 0, and these are the 2 points where it passes through 0. So if I make a little sign chart here at 2 and 4, I can pick values on either side, so 1, 3, and 5, and test the velocity. At t equals 1, if I plug 1 into the factored form, I'd have 3 times negative 1 times negative 3, which would give me a positive velocity. If I plug in 3, the velocity is going to be negative, and if I plug in 5, the velocity is going to be positive. So it's moving to the right on the interval 0 to 2 and 4 to 6. Okay? Because the velocity is positive on those intervals. So for part B, we want to know when is the velocity of the object increasing. So or decreasing rather. So to investigate whether the velocity is increasing or decreasing, we need to take a peek at the acceleration. Just change colors here for us. So the acceleration function is 6t minus 18. Again, set that equal to 0, and you'd have t equals 3. We can make a table of values here, or a chart rather, and plug in values on either side of 3. So the acceleration, if you plug in 1, Any number before 3, rather, the acceleration is going to be negative, and any number after 3, the acceleration is going to be positive. So the acceleration, the velocity is increasing on the interval 3 to 6 because acceleration is positive on that interval. Okay, and then similarly, velocity is decreasing on the interval 0 to 3 because acceleration is negative on that interval. Alrighty, so now let's look at the next one. When is the speed of the object increasing? So here's where we have to use that information that we had a little bit ago. Speed is going to be increasing when velocity and acceleration have the same sign. So in other words, when they're both positive and when they're both negative. So if we look at the intervals that we have and compare where they overlap, on the intervals 2 to 3 and 4 to 6, speed is increasing. And on the interval 0 to 2 and 3 to 4, speed is decreasing. And to justify that, for the increasing, you would say because speed, velocity and acceleration have the same sign on those intervals. And for the other two intervals, when the speed is decreasing, you would say because acceleration and velocity have opposite signs. Then finally, the last question asks, what is the average velocity? So to do that, for part D here, you would get 1 over 2 minus 0 times the integral from 0 to 2 of v of t dt, okay, which is going to be 1/2 integral from 0 to 2 of 3t squared minus 18t plus 24 dt. That's a half here. And then you'd have 1/2 times t cubed minus 9t plus 24t, evaluated at 0 and 2. And then that's going to be 1/2 times 20, which is equal to 10 units, would be feet per second. Now, for this one, to get average velocity, we could have used the original function, because the antiderivative of velocity is position. So we could have actually done x of 2 minus x of 0 all over 2 minus 0, and that would have given us the same result that we had a minute ago there for problem D. Okay, so let's look at another one, our last example here. We have the acceleration of an object on a horizontal line is given by a of t. We want to express the velocity as an integral. So for part A here, we know that the initial velocity is 2 meters per second. So v of t is going to be the initial velocity plus the integral from the initial time, which is 2, not 2. I accidentally wrote that in there. So let's erase this, fix that up. So v of 0 from 0 to t of a of t dt. Now, that would be enough. We could get more specific and write 2 plus the integral from 0 to t of t squared e to the negative t dt. For part B, v of 10, what's the velocity of the object at 10? That's going to be 2 plus the integral from 0 to 10 of t squared e to the negative t dt. Now we're going to actually get the value, but sometimes you might be asked to set up the integral that represents the position, and then that's all we would have right there for that one. So we're going to use Desmos for this one. So to get v of 10, it was the initial position, which was, or excuse me, the initial velocity, which was 2, plus the integral from 0 to 10 of v of t dt. So 3.994. So at t equals 10, the velocity is approximately 3.994 meters per second. Okay, so let's do part C now. What is the average velocity of the object over the first 10 seconds from 0 to 10? So I think this question meant to ask what is the average acceleration, because to get average velocity for this one here, you would have to do 1 over 10 minus 0 integral from 0 to 10 of v of t dt. But we don't have the specific function for v of t in this specific example right here. So what we could do, however, is try on Desmos. I have my acceleration function here, and our velocity function, which we defined earlier, is 2 plus the integral of acceleration. And I had to change the variable here because the upper limit is the variable x, and you have to integrate with respect to a different variable, which was already defined as t from the acceleration function. So then I plugged in the average value formula, 1 over 10 integral 0 to 10 v of x dx, and you get about 3.4. So if we take that as the average velocity, then we have that this is equal to 3.4. Now, to get the average acceleration, this is what I think the question meant. You would have to do 1 over 10 minus 0 times the integral 0 to 10 of a of t dt, which is 1/10 times. Now, remember, the antiderivative of acceleration is velocity, so that would be v of 10 minus v of 0. And then with that, we would have 1/10 times 3.994 minus 2, which comes out to approximately 0.199 meters per second. All right. So part D, at what time t is the acceleration of the object maximum? Okay, so for D, to figure that out, the acceleration function was given as t squared e to the negative t. The maximum value of acceleration is going to be when the derivative changes from negative or positive to negative. And also we got to check the endpoints because this is a closed interval from 0 to 10. So the derivative is, we've got to use a product rule. So t 2t e to the negative t minus t squared e to the negative t. The derivative of e to the negative t is negative e to the negative t. We could actually solve that for 0 using Desmos, or because you have factors of t here, you could factor out a t e to the negative t, and you would have 2 minus t equals 0. So this factor is equal to 0 when t is 0, and this factor is equal to 0 when t equals 2. And e to the negative t is never equal to 0. Okay, so we have t equals 0, t equals 2, and then t equals 10 is the right endpoint of our closed interval. 0 is not only a critical number, but it's the left endpoint, so we don't really have to check that twice. So here we have our acceleration function, and we're going to test it at a of 0, which is 0, a of 2, and a of 10. And clearly you could see that at 2 seconds, the maximum velocity is 0.541. So that is 0.541 meters per second squared. All right, guys, that's it for this one. Reach out if you have any questions. Hope that was helpful to you. Take care.